I want to keep talking about this idea of congruences and the set of equivalence classes, mod n, which we defined in the last video as Zn. And we'll show this in a second. But addition and multiplication behave exactly the same way that you'd expect them. So you can add two equivalence classes by just adding the members of them. And you can multiply two equivalence classes by multiplying the members of them. And remember, even if you get something that's bigger or smaller than the remainders here, remember the equivalence classes here contain all numbers that have that remainder. So you can just kind of change the representative for your equivalence class to 1 between 0 and n minus 1 if you like. So let's kind of show what's going on here. We'll show this works for real below, but let's work out the multiplication and addition tables for Z6, the integers modulo 6. So I'm going to do the addition table first, and I'm not going to put the brackets around my equivalence classes, just in the interest of space and brevity. 2, 3, 4, 5. They're the equivalence classes of Z6, or remember, maybe I'll write what Z6 is here. It is the equivalence class is 0, everything that has remainder 0, everything that has remainder 1, 2, 3, 4, and 5. Oh, and I put a comma in a weird place. Let me get rid of that. That's better. Okay. So, and again, I'm not writing the brackets for the equivalence classes. But let's see here. So remember our rule up here? To add equivalence classes, just add the elements inside them. So 0 plus 0 is 0. 1, 2, 3, 4, and 5. And since addition is commutative, well, the rows are going to be the same as the columns here. First row is the same as the first column. Now, for the most part, everything's going to remain the same. For the second row, we'll just add. We'll have to be careful with this last element here. So we have 1 plus 0 is 1, 1 plus 1 is 2, 3, 4, 5. And now we have, well, let's see what's going on here. This entry here we have to be just a little bit careful about. So we have the equivalence class of 1 plus the equivalence class of 5. And using our rule above, that's 1 plus 5, which is, of course, 6. But remember, this equivalence class has all numbers that have the same remainder as 6. And of course, when you divide 6 by 6, you get no remainder. So this is indeed the equivalence class of 0. And the reason I did that is I just want to pick the representative, so it's one we have in our set here, just so it's easier to read. So this is 0. Okay, and we keep going. 2, 3, 4, 5. 2 plus 4 is 6, which has remainder 0 when you divide by 6. 2 plus 5 is 7, that has remainder 1. And we can keep going. 3, 4, 5, 0, 1, 2. 4, 5, 0, 1, 2, 3. And 5, 0, 1, 2, 3, 4. So you can see how these work. In fact, let me do one more here just to make sure we understand what's happening. So let's do this guy, 4 plus 4. So this is the equivalence class of 4 plus the equivalence class of 4 is, of course, 4 plus 4, which is the equivalence class of 8. And out of the representatives we have listed, well, that's in the same equivalence class as 2, since they both have remainder 2 when you divide by 6. So that's the same as the equivalence class of 2. Okay, so just in the interest of space, so we have to do the multiplication table now. Maybe it's a good idea for you guys to pause the video, see if you can work it out in the similar way. Remember, here's our rule. The equivalence class of A times the equivalence class of B is the equivalence class of A times B. So do that out, see if you can come up with a similar table. So pause video now. I'm going to erase everything and change it to the multiplication table. So if you don't have this copied down, you should probably do that now. Okay, so here's the multiplication table. Let's work out the elements. Well, 0 times 0 is 0. In fact, 0 times anything is 0. So our first row and our first column is going to be the same equivalence class that 0 is in. And it's really saying, if you multiply any number by a number that's divisible by 6, that product is divisible by 6. That's kind of what this is saying. And multiplication by 1 gives you the same thing. 1 times 1 is 1. 1 times 2 is 2, 3, 4, 5, and down this way, 2, 3, 4, 5. 2 times 2 is 4. 2 times 3 is 6. But remember, for multiplying 2 times 3, we get 2 times 3, which is 6. And that's in the same equivalence class as 0. So we'll use the representative 0 to display that. 4 times 2 is 8, which has remainder 2. 2 times 5 is 10. That has remainder 4. Okay, and we can just do this, 0, 2, 4. And then 3 times 3 is 9. 9 has remainder 3 when you divide by 6. 3 times 4 is 12. That has remainder 0. 3 times 5 is 15. 15 has remainder 3. So we have 3, 0, 3. 4 times 4 is 16. 16 has remainder 4. And 4 times 5 is 20. 20 has remainder 2 when you divide it by 6. So put a 2 there. And finally, 5 times 5 is 25. And 25 has a remainder of 1. And again, let me just do one more of these so we understand what's going on here. So we have 3 times 5. That is, of course, 3 times 5 in its equivalence class, which is 15. But 15 is, of course, 6 times 2 plus 3. That's its remainder when you divide it by 6. So this is the same equivalence class as 3. So all that there is good. Okay, so we know how addition and multiplication works in Z6 anyway, and you can imagine doing a table up like this for any n. We just picked 6 as an example. Now, one thing that you could be wondering is, does this even make sense? Maybe if we take different representatives from our equivalence classes, well, maybe the product or the sum ends up in a different equivalence class than with 2 other representatives. How do we know that? So that's something we have to show. And that's what we're going to do here. We're going to show that addition and multiplication are well-defined modulo n. And remember, what does well-defined mean? It means that if we take 2 elements and we apply the function to it, and those 2 elements are equal, then the function value is equal. And we're going to think about this as a function. So if we think about it, addition, well, we're going to take two elements from Zn and add them together. So it's going to be a function where the domain is Zn cross Zn. Just like here, Z6, we were taking two elements and adding them together. So it goes from Zn cross Zn to Zn. And it's defined by, of course, I'm going to write it in function notation. It's going to look weird. Of course, we write it differently. But if we call this function plus, it's plus of the equivalence class of A, the equivalence class of B. That equals the equivalence class of A plus B. And of course, we don't write it like that usually. Usually we write the equivalence class of A plus the equivalence class of B. But it really is a function. Okay. We need to show that if we pick two different representations for our equivalence class, maybe we don't want the representatives 2 and 3, maybe we wanted, say, 8 and 9 or something like that, we'd still end up in the same equivalence class. So with addition, let's go ahead. So we're going to let A1 equal A2. So they're not the same representative potentially, but they are the same equivalence class. Like in Z6, maybe A1 is 0 and A2 is 12. Everything that has a remainder of 0 can be a representative for the equivalence class of 0. And let's let B1 equal B2. Same idea. Okay. So what do we want to do? We want to show that if this is indeed well-defined, we want to show that if we apply the function and we get the equivalence class of A1 plus B1, that's the same equivalence class as A2 plus B2. And remember, things are in the same equivalence class when they have the same remainder. Or, equivalently, if you subtract these representatives and you get that it's divisible by n. So that's what we're going to do. Let me scroll down here. Okay, so since these equivalence classes are equal, A1 and A2 by assumption, we know that A1 and A2 are related. So A1 is related to A2. That's great. Okay, since A1 is related to A2, this means, let's get rid of that 2 there. This means that n is a factor of A1 minus A2. And let's indeed show that A1 and A2 have the same remainder. Why not? Okay, so what does this mean? Thus, A1 minus A2 is n times c for some integer c. So A1 minus A2 is some multiple of n. Now, by the quotient remainder theorem, I'll call it QRT, we have that A1 is Q1 times N plus some remainder. Call it R of A1. And A2 is Q2 times N plus R of A2. In fact, maybe I'll call these Q of A1 and Q of A2 as well. For QA1, QA2, RA1, and RA2 that are integers, and of course RA1 and RA2 are proper remainders. So they are at most the absolute value of n exclusive of n and inclusive of 0. Okay, so what does this mean? Well, let's write A1 minus A2 like that. Thus, A1 minus A2 is, well, QA1 times N plus RA1 minus QA2 times N plus RA2. And we can simplify that and collect anything that has an N. So let's go ahead and do that. We'll factor with the N out of those terms, and we get QA1 minus QA2. And then we have plus RA1 minus RA2. And so this is a good time to use a without loss of generality argument. I'm just going to say that A1 is the number that has the bigger remainder. So without loss of generality, let RA1 be greater than or equal to RA2. Okay. So here, remember that A1 minus A2 we said already equaled N times C. So this means that, well, we have N as a factor of this term, and N is a factor of the entire right-hand side, so N must be a factor of the second term on the left-hand side. So since the right-hand side, or let's say N is a factor of the right-hand side, N must be a factor, or N must divide, the left-hand side of our equation, and thus, since N is a factor of the first term, N must be a factor of the second term, RA1 minus RA2. Now, remember, we wanted to show that these guys have the same remainder. So pause the video and see if you can convince yourself why these numbers have to be equal. Remember, N has to be a factor of them. Okay, now that you're back, remember, the biggest any of these remainders can be is N minus 1, or the absolute value of N minus 1. So what does that mean? Well, that means that if RA1 is the bigger one, the biggest this expression can be is, of course, n minus 1. But remember, this has to be divisible by n. And if it's divisible by n, the only way that this is possible is if these numbers are equal. So, since we know that this expression here, this difference of remainders, has to be between 0 and the absolute value of n minus 1, it must be that RA1 minus RA2 equals 0, and thus they're the same. RA1 equals RA2. And in fact, maybe let's call this a little lemma, because we talked about this in a previous video, but we really didn't prove it. So let me go here, and I'm going to call this a little lemma. And a lemma is just a mathematical result that's used to prove other mathematical results. So this is going to be our lemma. It's kind of a mini theorem. And it basically says that if you have two elements, say x and y, that are in the same equivalence class, mod n, then x and y have the same remainder. So that's what we kind of showed in this argument here. And now, because we have this called a lemma, I can keep referring to this if we need it. So we finished that little lemma, and we can go back to our main result here. Okay, by our lemma, so by the lemma, we know that since A1 and A2 are in the same equivalence class, they could be representatives for the same equivalence class. This means that we can write A1 as QA1 times n plus R of A, and A2 equals Q of A2 times n plus R of A. And note that there's no extra subscript on that A here, because I know by that lemma the remainders are the same. This is just a remainder for those A terms, because we were saying that A1 and A2 were in the same equivalence class, so they have the same remainders. And, well, we can apply the lemma to the B's as well. So, and since the equivalence class of B1 equals the equivalence class of B2, these guys have the same remainder. B1 equals Q of B1 times n plus R of B, and B2 equals Q of B2 times n plus R of B. And again, the key is they're in the same equivalence class, so they have the same remainder. Now, let's just consider both A1 plus B1 and A2 plus B2. So the equivalence class of A1 plus B1, well, this is going to be the same thing as the equivalence class of, well, A1 is QA1 times n plus RA, And B1 is QB1 times n plus r of b. So again, that's just using the quotient remainder theorem to write A1 and B1 as so many multiples of n plus a remainder. And let's simplify this. So let's group together our things that have n's in them, and that is indeed these first two terms here. So this is n times QA1 plus QA2 plus RA plus RB. And of course, well, this is just a bunch of multiples of n added to RA plus RB, so it's not going to change that remainder at all. So this is indeed just the same equivalence class as RA plus RB. Okay, and similarly, we know that A2 plus B2, well, just doing the same argument here, except replacing the A1 and the B1 with A2 and B2, we get literally the same thing. This is also RA plus RB. So, since A1 plus B1's equivalence class is the same as RA plus RB, and so is A2 plus B2, thus A1 plus B1's equivalence class is the same equivalence class as A2 plus B2's equivalence class. Okay, so we did the result here for addition. Let's do it for multiplication. And in fact, maybe it's a good idea for you guys to pause the video and see if you can do it. So remember, we want to show that the equivalence class of A1 times B1 is the same as the equivalence class of A2 times B2. So remember, we have that lemma to use. We can use the fact that A1 and A2 have the same remainder, and B1 and B2 have the same remainder. So maybe pause the video, do the same type of argument as the above, and see if you can get it to work. Okay, now that we're back, well, we have to consider A1, B1, and remember, we wrote A1 as Q of A1 times N plus R of A, and B1 is Q of B1 times N plus R of B. So let's expand this out, and what's going to happen is the only thing that we are going to have that doesn't have a multiple of n is this RA times RB term. So let's go ahead and do that. So we're just going to use distributivity. So this is going to be QA1n times QB1n. So the first term is QA1 times QA2 times n squared. I don't really care too much about this bit. All I care about is that there's one n in that term. Plus, let's do the next one. So this is QA1 times RB times n. And then the next one is QB1 times RA times n. And the last term in our multiplication is RA times RB. Again, we're just using distributivity. There's a first term There's our second term. Here's our third term. Here's our fourth term. And of course, the key thing is that the first three terms have a factor of n. So let me factor this out. So we have n times qa1, qa2 times n, that's the first term, plus qa1 times rb plus qb1 times RA, and that's everything that had a factor of n, the first three terms, just factored out the n out of them, and we're left with this RA times RB term, which may or may not have a factor of n. If one of the remainders is 0, then for sure it will be, because that term will be 0. So remember, this bit here, all of this is just a big old multiple of n. So if you add a multiple of n to some number, it's not going to change the remainder of that number. So this is the same as just RA times RB. So the remainders for this number here, which is some multiple of n plus RA times RB, and just RA times RB itself, well, they're of course going to have the same remainder. So they're in the same equivalence class. So they can be represented by either element. And similarly, we have that A2, B2 is the same equivalence class as RA times RB, just multiplying those remainders. So what does that mean? So that means that the equivalence class of A1, B1 is the same as the equivalence class of A2, B2. So what did we just show here? We showed that if we had different representatives for our equivalence classes, it doesn't matter. Our answer still ends up in the same equivalence class. So that's really cool. This is indeed a well-defined operation. And we did that for both addition and multiplication. Okay, let's switch gears just a little bit. We're still talking about divisibility, but let's show this little result here. We have some integer c. And we want to show that if 3 is a factor of c squared, then 3 is a factor of c. Now, the converse of that, I think, is very easy to prove. If we said if 3 is a factor of c, then 3 is a factor of c squared, you could do that as a little exercise. But the other way, it's not particularly difficult, but you have to think about the best way of proving it. So maybe pause the video and see if you can come up with a good strategy for showing this. Okay, now that we're back, the problem is if we try and do a direct proof of this, it's really hard to kind of take that square root and see how that affects things. So a direct proof might not be the best way of going. So let's write down the contrapositive proof. So let's prove this by contrapositive. Okay, so let's assume that 3 isn't a factor of c. Now that we talked about the quotient remainder theorem, we have a way of writing 3 isn't a factor of c. It means it has a remainder of 1 or 2 when you divide it by 3. So we'll have two different cases here. This means that we can write c as q groups of 3 plus 1, or we can write c as q groups of 3 plus 2 for some quotient q. So for some integer q. Because remember, the only remainders when you divide c by 3 that are possible are 0, 1, and 2. We're assuming it's not 0. We're assuming that 3 isn't a factor of c, so the only possibilities are 1 and 2. So we have two cases. So let's do case 1, which is when our remainder is 1. So let's consider c squared, which is q times 3 plus 1 squared, which is, and I'll just write this out. You can check that this is true, but it's 9 q squared plus 6q plus 1, which I can write as 3 times an integer, and that integer is 3q squared plus 2q plus 1. And by the quotient remainder theorem, well, we have a remainder of 1. And that remainder is unique. So it's the only way of writing c squared as a multiple of 3. So thus, 3 isn't a factor of c squared since we have that remainder. And case 2 can be very similar, is when r is indeed 2. Let's do the same thing. Let's consider c squared, which in this case is q times 3 plus 2 all squared. And again, I'm just going to write this out. You can check that this is true. This is 9q squared plus 12q plus 4. And I can write that in quotient remainder form as 3 times 3q squared plus 4q plus 1. Since I have this 4 here, I can take out a 3, so there's my 1, 3, and I have a remainder of 1 left over. And again, I have this remainder of 1, so that tells me that 3 isn't a factor of c squared. And we're done. We did both cases here. I do want to point out one cool thing. And that cool thing is that it shows that if you have an integer, then the square of that integer, if you divide it by 3, is only going to have remainder 0 if it is divisible by 3, or 1 if it isn't divisible by 3. No square number has a remainder of 2 when you divide it by 3. So that's quite interesting. Anyway, this is a good method of approaching some problems if you're dealing with divisibility and you don't like squares or cubes or something. Remember, you can look at the contrapositive and just do some cases for the different remainders.